In this video, I'll be solving a fairly challenging problem involving a chain falling off of a table. So let me just read the problem. A chain with a total length L initially is at rest with a length of X hanging off a frictionless table. At the instant when the last link of chain slides off the table, the chain is moving downwards with a speed of V. So ignoring air resistance, find V, and then it's giving us a couple numerical values. So first thing I'm going to note is just that it says explicitly initially at rest. So I'm just going to write for future reference that means the initial velocity is 0, right? So it starts not moving and then it's released and then it will fall off the table. Okay, and then the question is saying, let's see, at the instant when the last link of chain slides off the table. So if you can imagine, I guess I'll just kind of draw it in white. So at some instant, the chain will be, I'm drawing it a little far away from the table, but at some instant, the chain will be right there. The last link will have just fallen off. So what is the speed in that case? So what that is basically saying, that is saying when x, which is the distance that the chain is hanging off the table, when x is equal to L, which is the full length, what is the speed? So I'll say when x is equal to L, what is V? Oops. What is V? So that is what we're looking for. So how I'm going to approach this is I'm going to use energy, because there is well, for one, it's asking us for speed, so energy is something that you should consider when solving for speed. But there's also a change in height, right? The chain starts on the table and it's falling off of the table. So the height is changing, aka the potential energy is changing. So that is going to be my approach. So I'm first just going to write the conservation of energy, just to start looking at it. So I'll say that the initial kinetic energy plus the initial potential energy is equal to the final of both of those quantities. And like it says, the table is frictionless, ignore air resistance, so we don't need to worry about friction. And obviously there's no spring or anything like that, so the potential energy is purely gravitational. Okay, well, we can immediately cross out this term because the initial speed is 0, right? It starts from rest, so there's no initial kinetic energy. And then this term is just going to be, the regular 1/2 mv squared. And that's what we're trying to solve for. We're trying to solve for V. So the trick is to find out an expression for the potential energy. So what I'm going to do is I'm going to zoom in a little bit and just hone in on a little tiny piece of the chain. Let's say just one link. Oops, that's a circle. Even though I'm imagining that it's a very, very, very small piece of the chain, but you can think of it as just one link. So I'm going to blow this up over here. And I'll draw it a little bigger. Okay, so that square that I just drew is going to be a small, very small piece of the chain. So small that the height right here is actually dy. This height is dy. And the mass of this little piece of the chain is going to be dm. So small that I've introduced differential elements. Okay, so now, well, let me just write down, so potential energy, gravitational potential energy is mgy. That's the generic formula for gravitational potential energy. So this piece of the chain is going to have some gravitational potential energy of dm times g, not dy though, it's just going to be y, because y is our variable, right? And this thing is falling off the table, and y is going to be different for every piece of chain. So I'm going to call, let's see, I'm going to call this distance, or this height, this is going to be my reference height. So y is going to equal 0 here, which means that as the chain falls off the table, it is getting, its potential energy is getting more and more negative. Okay, so I'm going to say that this equation right here, this equation right here, this is the formula for the gravitational potential energy of that little piece of chain. So the very small bit of gravitational potential energy at one instant. Okay, so as you can see, hopefully we're gonna have to integrate. Except for the only problem is the variable that's changing is y, right? So at a different instant, the y will be a different length. So we need a way to relate dm and dy. So let me bring up the density equation. So that would be rho for density. That just equals mass per volume. Except in this case, since the chain is basically a one-dimensional, we're thinking of it as a one-dimensional object, we could say mass per length, which is, it's the same concept, it's just one-dimensional density, essentially. So we could say that density of the chain is the total mass compared to its total length. But that is the same thing as saying a small bit of mass compared to a small bit of length. Small bit of length, which I'll call dy. So that's just saying rho, the density, it does equal, it's the total mass over the total length, but it also equals the mass of the small little link right here, compared to the length of it, which is dy. So we can solve for dm by multiplying both sides by dy, and we get that dm is equal to m over L dy. So now, if I plug this back in to this little bit of potential energy equation, I get that dm is, well, m over L dy times g times y. And remember, our variable is y, so that was the reason why I wanted to get the dy in there, because we're going to be integrating over the length, which is y. Okay, so now we can say, okay, to get the total the total gravitational potential energy, we're just going to integrate both sides. You do that in blue. So integrate this side, integrate this side, and I'm just going to rewrite it a little better down here. So that's going to say that the gravitational potential energy is equal to the integral, I'll deal with the limits in a second, but it's the integral of m over L times g and then times y dy. So that's the variable and that's our differential element. Okay, so the limits of integration. So remember, this is asking for when the last link of the chain is just, sorry, when the last link of the chain has just fallen off the table. So at that instant, x is equal to L, right? That's what we're trying to find. So when we integrate, we want to go from, so here, let me just redraw the chain like this. So this is going to be at the instant when the chain is down. So we want to integrate from this point to this point. Well, this point up here is just 0 because we called that y equals 0. So 0 is going to be our upper limit. And then down here, if this length right here is x, which by the way, x of course is changing, right? At a different instant, there'll be, if this is the table, there'll be a couple of links left and the rest of the chain is down here. X is the distance that the chain is hanging off. So at the last instant, this position down here is going to be x, but negative x. And the reason why it's negative is because it's below the y equals 0 line. So that's going to be our lower limit. We're going from negative x to 0. I'm just going to erase this. Okay, so now this is something that we can integrate. So I'm going to, well, for one, I'm going to pull out those constants. So we just get mg over L times, so we're just integrating y with respect to y. So we're going to get a 1/2 y, 1/2 y squared. And that's being evaluated from negative x to 0. Okay. So now we just plug in, so we'll say mg over 2L, both of those look like L's, 2L, so those are the constants, and then we have, well, 0 squared, which is 0, minus, and then we're plugging in negative x, and we're squaring it. So what we get is, so this negative x squared becomes positive, but then we're subtracting it off. So what we get, I'll write it down here, is that the potential energy is equal to negative mg over 2L x squared. So now we have a formula for potential energy that relates x and L. So now the next step is to come back over here. So what we really wanted was to find an initial and a final expression for the potential energy. So still have a little bit of reasoning left. So the initial potential energy, right, is going to be, well, this x squared, initially it's just like this. So the x squared, of course, stands for the length that is hanging off. So initially, x is just, well, x, right? X stands for the amount of length that's hanging off, and there is x amount of length hanging off at the beginning. So the initial potential energy is just going to be negative mg over 2L x squared. And that's equal to 1/2 mv squared, which we're trying to solve for v. And then the final kinetic energy, the final potential energy. So up here, I wrote down, what we're trying to find ultimately is when x is equal to L. So when the distance that's hanging off the table is the whole length, L. So in this equation, we're going to substitute an L for x because that is saying that the amount hanging off the table is the whole length, which is L. So we're going to say minus mg over 2L times L squared. Okay, so now we are just going to algebraically solve for v. So first off, this L will cancel with that L. And secondly, the mass is going to cancel out of every term. And if you notice in the beginning, the mass wasn't a part of the question, so we hoped that it would cancel somewhere in the problem. So let me just rewrite. So we have negative gx squared over 2L is equal to 1/2 v squared minus gl over 2. So now, solving for v, I'm going to move this term over here, and I'm also going to multiply by 2. So, actually, let me just do that in 2 steps. So 1/2 v squared is equal to, so I'm making this term on the other side, or it's positive on the other side. So it's going to be GL over 2, and then minus GX squared over 2L. Okay, so if you notice, if I multiply everywhere by 2, every 2 is just going to cancel. So I'm essentially just going to cancel all the 2's. And then the last step is to just take the square root to solve for v. But at the same time, I'm also going to factor a g out just to make the calculation slightly easier. So v is going to equal the square root of g times, well, it's going to be L minus x squared over L. So that is the formula for v, and it's just in terms of L and x and g. Well, we know g, and the only values that it gave us up here are L and x. So now we can solve for v. So just plugging in the numbers, v is equal to the square root of 9.8 meters per second squared times L, which I believe is 2 meters. I'm going to go check that in a sec. 2 meters minus x, which I think is 0.5 meters squared, divided by L, which is 2 meters. Just going to check up here. L would be 2 meters. Yep, okay. So now we just need to crunch the numbers. And I did this on the side, but if you crunch the numbers, you're going to get v is 4.29 meters per second. And there's the answer.